Okay, so maybe it's time to start. Today we have a talk by Anton Shafarevich on flexibility of affine spherical varieties. So, Anton, please.
Okay, so everyone can hear me and see my presentation, right?
At least I do.
Okay, thank you. First of all, I would like to thank the organizers for the opportunity to speak at this seminar. And I will start with the basic definitions. So let G be a group acting on a set X. And for an integer m, we say that this action is m-transitive if for any two ordered m tuples of pairwise distinct points, x1, x2, up to xm, and y1, y2, ym in X, there exists G such that gxy equals yi for all I. Let's consider some examples. The action of the automorphism group of affine line acts on affine line two-transitive, but not three-transitive. We know that the group of automorphisms of affine line is just it consists of affine transformations, and as we understand, it's two-transitive, but not three-transitive. The action of the automorphism group of P1 projective line on P1 is three-transitive, but not four-transitive. It's trivial that we can move any 3 points of P1 to any other 3 points of P1, but we cannot move any 4 points of P1 to any arbitrary any other 4 points on P1 because we have an invariant on P1. The action of automorphism of Pn on Pn when n is at least 2 is two-transitive, but not three-transitive. If we choose 3 points which lie on the same line in Pn, then we cannot move these 3 points to 3 points which do not lie on the same line. So we say that an action of G on X is infinitely transitive if M is transitive for all M. And further, I will assume that ground field is algebraically closed and of characteristic 0. Let's consider an algebraic group G and suppose it acts on algebraic variety. Then it's easy to see that this action cannot be infinitely transitive. Because let's take 1 point, x1. If this action is infinitely transitive, then the stabilizer of this point, gx1, acts transitively on x minus x1. Again, if we choose some point x2, then the subgroup gx1, x2, which stabilize both these points, x1 and x2, acts on x minus x1, x2 transitively, and so on. So we obtain the chain of subgroups. G contains gx1, contains gx1, x2, and so on. And all inclusions are strict. So this is a contradiction because finite dimensional algebraic group cannot have such chain of subgroups, such infinite chain of subgroups. And actually, there is a theorem that any action of a linear algebraic group on algebraic variety is at most three-transitive. And moreover, the only three-transitive action is the action of PGL2 on P1. So it is it was proven by Tits in the context of Lie groups over the field of complex numbers, and by Knopp over arbitrary algebraically closed field. And actually, they both gave all the classification of all transitive actions of algebraic groups. Now let's consider an example of infinitely transitive action. Consider the affine line A2. And let us choose two m tuples of distinct points. A which consists of points A1, A2 up to AM, and B, which consists of points B1, B2 up to BM. So suppose that the point AI has the coordinates xi and I and yi, and the point BI has the coordinates zi, wi. And one can choose coordinates in A2 such that the first coordinates x1, x2 up to xm are pairwise distinct, and the second coordinates of y1 and the second coordinates y1 and so on are also pairwise distinct. So all coordinates are pairwise distinct. Then we can consider the following action of the group GA on A2. And by GA, I will always mean the additive group of the ground field K. So with respect to this action, an element S from GA acts on a point xy, x and y by the following formula. So we fix first coordinate and the second coordinates. Well, it's written how it changes. And it's easy to see that it is indeed a GA action on A2. Moreover, we see that the points AI with I from 1 to m-1 are fixed. When we apply this action to points AI, they are fixed. And the last point AM is not fixed. And we have an element S0 of GA such that S0, the result of S0 on AM is a point XM So let's consider a picture. So we have blue points A1, A2, etc., AM, and red points. And we have GA action which moves AM to a point as 0 AM, which has the same second coordinate as the red point BM. And also we have a GA action which will move this point as 0 AM to BM. So the composition of these automorphisms fix all blue points except AM, and it moves AM to the red point BM. So we can move AM to BM, then we will move AM-1 to BM-1, and so on. So we see that the group of automorphisms of affine plane acts infinitely transitive on affine plane. And let me give the main definition here. Let X be an irreducible affine algebraic variety. Then a smooth point X is called flexible if the tangent space at this point is spanned by the tangent vectors at X to the orbits of all GA actions on X passing through X. And the variety X is flexible if all points in X are flexible.
Bad information.
This is a set of all smooth points in X. So denote by SAut of X the group in out of X generated by all GA subgroups. And there is a theorem by Arzhantsev, Flenner, Kaliman, Kutzschebauch, Zaidenberg. Let X be an affine reducible algebraic variety, and dimension of X is at least 2. Then the following conditions are equivalent. X is flexible, the group SAut of X on X-raj transitively, and the group SAut of X on X-raj infinitely transitively. So if the group SAut of X on X-raj transitively, then this group actually X on X-raj infinitely transitively. When dimension of X is equal to 1, then if we have at least one GA action, then X is just a affine line. And we still have the equivalence of first 2 points. X is flexible, and the group SAut of X acts transitively on smooth points, but in this case, not infinitely transitively. So what examples do we have? So as we see, affine space is flexible for any n. By GA actions, we can move any point to any other point. If we consider a semi-simple group GS, then GS is flexible. Well, indeed, because any semi-simple algebraic group generated by its root subgroups, and root subgroups are isomorphic to GA. So any semi-simple algebraic group generated by GA subgroups. And so this group SAut of GS acts on GS transitively. So it's a flexible algebraic variety. And moreover, if we consider not a semi-simple algebraic group, but a smooth reducible affine algebraic variety, such that a semi-simple algebraic group acts on X with an open orbit, then X is flexible. It is a theorem, again, by Arzhantsev, Flenner, Kaliman, Kutzschebauch, Zaidenberg. And we will return to this theorem later. We will discuss how this theorem can be proven. Let's consider an example of not flexible algebraic variety. The algebraic torus k star to the power n is not flexible. Well, and it is easy to see because the automorphism group of algebraic torus, this torus is the semi-direct product of this torus and the group GLN of Z. And there are no non-trivial GA actions on torus. So the automorphism group just does not contain any GA subgroups. So what are the abstractions to flexibility? Why some variety cannot be flexible? Consider a function f which is invertible on X-range. Then any GA orbit is either a point or isomorphic to A1. Since there are no non-constant invertible functions on A1, the restriction of f to any GA orbit is a constant. Hence, if X is flexible, then f is constant on X-range. So invertible functions, they are invariant with respect to all GA actions. So we obtain if X is flexible, then the group K of X-range cross equals to K cross. Well, here I denote by cross the group of invertible elements. Well, and in particular, if X is normal and flexible, then K of X cross equals to K cross. Because if X is normal, then the algebra K of X coincides with the algebra K of X range. But it is not a sufficient condition. If you consider the Danielewski surface, which is given by this equation, x square z equals to y by y plus 1, it is not flexible, but k of x range cross equals to k cross. Well, it's not difficult to see that it is not flexible. The automorphisms of Danielewski surface are well known, and one can directly check that it is not a flexible variety. And let's give some more example of flexible varieties. So consider a flag variety G mod P, where G is a semi-simple algebraic group and P is a parabolic subgroup in G. Then every normal affine cone X over G mod P is flexible. It is a theorem by Arzhantsev, Kaliman, Zaidenberg. And if X is an affine toric variety, and k of x cross equals to k cross, then x flexible. And also suppose we have a flexible variety x and f is a non-constant function on x. Then the variety yz equals to f of x is flexible. Such varieties are called suspensions. So we have some wide classes of flexible varieties. Normal affine cones over flag varieties, affine toric varieties without invertible functions except constants. And if you have some flexible variety, we can construct more flexible varieties by this operation suspension. And first two varieties in this example are spherical variety. Let me give the definition. Let G be a reductive group and B be a Borel subgroup in G. An irreducible normal algebraic variety X with an action of G is called spherical if there is an open B orbit in X. So obviously, if you have an open B orbit in X, then we have an open of G orbit in X. Well, and it's easy to see that toric varieties are spherical varieties. In case when G is a torus, then Borel subgroup B is equal to G. It is also a torus. And so this is Borel subgroup acts on toric variety with an open orbit. And similarly, flag varieties are also spherical varieties. Because if you consider a flag variety G mod P, and we choose a Borel subgroup P inside P, then we have the opposite Borel subgroup B minus. And this B minus acts on G mod P with an open orbit. And even if we consider a normal affine cone over a flag variety Z, it also will be a spherical variety because we can act on this cone by one-dimensional torus. So we have the action of G plus we have one-dimensional torus which acts on cone. And this direct product of G and this one-dimensional torus acts on this variety with an open orbit, and Borel subgroup will also have an open orbit. So these are the examples of spherical varieties. There is one more interesting example of spherical variety. Let G be a reductive algebraic group, then G times G acts on G by left and right multiplications. Let us choose a Borel subgroup B in G and denote by B minus the opposite Borel subgroup. Then there is an open B times B minus orbit in G, which is a big cell B minus. Therefore, G is a spherical variety with respect to this G times G action. And moreover, any G times G equivalent embedding of G is also spherical variety. And I want to note that affine G times G equivalent embeddings of G, it is an algebraic monoid of, with a reductive group of invertible elements. So one more class of spherical varieties is orospherical varieties. When a reductive group G acts on an affine variety X, the algebra K of X has the following decomposition. It's a direct sum of irreducible G modules, and I denote by W lambda an irreducible G module with the highest weight lambda. But note that the same lambda may appear several times. When an arbitrary reductive group acts on affine variety, then the same lambda may appear several times. And actually, the variety X is spherical if and only if each lambda occurs no more than once. And in this case, this decomposition is unique. So in a affine case, there is another description of spherical varieties. It's such varieties that the algebra of regular functions has such nice decomposition. So it's a direct sum of irreducible G modules, and every irreducible G module appears no more than once. And the next definition, a normal irreducible algebraic variety X with an action of a reductive group G is called orospherical if there is an open G orbit O in X, and the stabilizer of any point X contains a maximal unipotent subgroup of G. Toric varieties and flag varieties are orospherical. And it's important class of subclass of spherical varieties because in this case, this decomposition one is actually a grading. So for orospherical varieties, this decomposition is a grading of algebra K of X. And there is a theorem that for a semi-simple algebraic group G, any affine orospherical variety is flexible. And by definition, spherical varieties are normal. But actually, we can consider not only normal varieties and give the same definition of spherical variety for non-normal varieties. And with this definition, actually, this theorem also holds. So here we consider not only normal affine varieties. And later, with joint work with Sergei Gayfulin, we proved that for a reductive algebraic group G, any affine or spherical variety X with K of X cross equals to K cross is flexible. But here we assume normality. So here we need X to be a normal variety. And Ilya Boldarev and Sergei Gayfulin proved that a non-normal affine toric variety X with K of X range cross equals to K cross is flexible. And there's a recent work by Sergei Gayfulin and Veronika Kikteva. Then a normal affine or a spherical variety with K of X range cross equals to K cross is flexible. So there were several results about flexibility of spherical varieties. So it started with flexibility of toric varieties. Then it was generalized for orospherical variety. And there was a conjecture that any affine spherical variety with K of X cross equals to cross is flexible. And this is true. This is the main theorem of my talk, that an affine spherical variety X with K of X cross equals to cross is flexible. And here I assume that X is a normal variety. I'm sorry, I need to check one thing. I'm sorry.
Anton, up to now, everything was okay with the screen.
Okay, yes, I just don't see time, so okay, but never mind.
You spent just a half an hour. So the talk was broken at the main result. This is rather dramatic. Okay.
Thank you. So let's continue. Can you see me, my slides again? Yes.
Yes, we do.
Mm-hmm. So I will discuss the main ideas of the proof. The proof actually is not very complicated. So the first proposition, let G be a linear algebraic group acting effectively on affine algebraic variety X. And suppose that the group generated by G and SAut of X acts transitively on X range. Then we assume that K of X range cross equals to K cross. Then SAut of X acts transitively on X range and X is flexible. So actually, when we need to prove that some affine variety is flexible, we can use some actions of algebraic group. If not just SAut of x extransitively on x range, but this bigger group generated by G and SAut of x extransitively on x range, then actually x is flexible. And it will be helpful, of course, because when we have a spherical variety, then we have an action of a linear algebraic group. And I will discuss the proof of this proposition again later, but I want to just briefly explain the main structure of the proof of the main theorem. So suppose we have this proposition, and to prove that affine spherical variety x is flexible, we need to prove that this group generated by G and SAut of x acts transitively on the set of smooth points. Let X be an affine spherical variety with an acting reductive group G. Let B be a Borel subgroup in G. Then for any G orbit Y in X range, there is an open B invariant subset XY intersecting Y and having the following properties. Later I will explain what is this subset XY. But now just say what properties do we have. So there is a reductive subgroup L and G and a closed L invariant subset Z in XY, such that XY is isomorphic to the direct product of affine space and this subvariety Z. So this open B invariant subset actually just a product of affine space and Z. And this subvariety Z is affine smooth spherical variety with respect to the action of L. So this this B invariant subsets XY are useful because they have such nice structure. It is a product of affine space and some smaller, usually smaller spherical variety Z. And when Y is a smooth orbit, the Z actually a smooth spherical variety. And then
there is a question from Stephanie. Anton, and there is a question from Stephanie.
Sorry.
Whether do you assume that the acting group G is connected?
Yes, sorry. Yes, it's yes. Thank you. Yes, I always assume that all reductive groups are connected. Yes, thank you. Then we will prove then the group generated by L and SAut of Z acts transitively on Z. And it automatically implies that the group generated by L and SAut of XY also acts transitively on XY. So we will prove that this subgroup L generated by L and SAut of Z acts transitively on Z. And of course, because if XY is a product of affine space and Z, then the group generated by L and SAut of XY acts transitively on XY. So on these open subsets XY, we have that the subgroup acts transitively. And
again a question concerning this local structure theorem. So whether you assume that Z is smooth?
Well, I assume that Y is smooth. So my G orbit Y consists of smooth points, and it implies that Z is smooth. So so the fact that Y consists of smooth points leads that Z must be smooth. Smooth. Sorry. So and one more thing. Actually, this open subset is an principal open subset. So there is a regular function f such that well, this open subset xy equals to the set of points where this regular function is not equal to 0. And it implies it's some, well, it's not difficult to prove that in this case, for any GA action alpha on xy, there is a GA action beta on x, such that for all x from xy, the alpha orbit of x coincides with a beta orbit of x. So this it's just a fact about principal open subsets. If we have some GA action on a principal open subset, it is not necessary that this GA action can be extended to the whole variety X. But actually, we have a similar GA action on X, such that the orbits inside XY are the same. And this implies that this subset XY is contained in a single orbit of this group generated by G and SAut of X. Because before we saw that this subgroup L and SAut of XY acts transitively on XY, and since XY is a principal open subset, for any GA action on XY, we have the similar GA action on X. So we obtain that this group G, so this subset XY is contained in a single orbit of this group generated by G and SAut of X. And all these open subsets intersects, and any smooth point belongs to some orbit Y. So by an action of G, we can move any smooth point to some point inside XY for some orbit Y. And all these sets XY intersects. So we obtain that this group generated by G and SAut of X acts transitively on XH. And actually, in fact, XY is isomorphic to the product of an affine space and algebraic torus. Actually, one can prove that the structure of these subsets actually is very simple. It's just the product of an affine space and algebraic torus. Well, this is the main ideas of the proof. And now let's discuss how some points of this plan can be proved. And I need to recall some basic construction, which is well known, but I still want to recall because it's important. It's about homogeneous fiber bundles. Let G be a linear algebraic group and H a closed subgroup. Then for a quasi-projective variety Z with an action of H on Z, one constructs the homogeneous fiber bundle G times Z over H. The construction is following. Consider the action of H on G times Z. So as if written, H acts on GZ by the following formula. Then this homogeneous fiber bundles is actually the geometric quotient of G times Z by this action of H. It's not obvious that this geometric quotient exists, but actually it exists, and it is an algebraic variety. And for a point GZ from product of G and Z, I will denote by brackets the image of these points in this homogeneous fiber bundle. And why it is called homogeneous? Because our group G acts on the product of G and Z by left multiplications on the first factor. And this action obviously commutes with our actions of H on this product. So actually, the group G acts on this homogeneous fiber bundle, G times Z over H. And we have the map, which sends the image of a point GZ to a coset GH. And it's not difficult to check that this map is G equivalent fiber bundle over G mod H, over the homogeneous space G mod H, with the fibers isomorphic to Z. So the structure of this homogeneous fiber bundle is the following: we have a homogeneous space G mod H, and this fiber bundle is fiber bundle over G mod H with and fibers are isomorphic to Z. And actually, when Z is an H model, then this fiber bundle is just a vector bundle. So let's go back to the first proposition. Let G be a linear algebraic group acting effectively on affine algebraic variety X. And suppose that the group generated by G and SAut of X transitively on X range, and K of X range cross equals to K cross. So we want to prove that SAut of X actually acts transitively on X range. So as we know, we know that G is a semi-direct product of reductive group G and the unipotent radical Ru. And the reductive group is an almost direct product of a torus T and a semi-simple algebraic group. And since the unipotent radical is generated by GA subgroups and semi-simple part generated by GA subgroups, then the group generated by G and SAut of X is the same group as the group generated by T and SAut of X. So suppose that the action of SAut of X on X range is not transitive. The orbits of SAut of X are locally closed. It's not obvious, but it was proven in original paper of Arzhantsev, Flenner, Kaliman, Kutzschebauch, and Zaidenberg. So they actually proved that the orbits of this group SAut of X are locally closed. And denote by Y one of the SAut of X orbits in X range. So we can consider a subgroup S inside T, which preserves this orbit Y. So such elements T, such that Ty equals to Y. Then we have the map from homogeneous fiber bundle T times Y over S to X range, which send the image of a point Ty to the result of the action of T on the point Y. And it's not difficult to check that it is a well-defined map, and actually it's an isomorphism. So in this case, actually our set of smooth points X range is just a homogeneous fiber bundle T times Y over S. So, and if S is not equal to T, then, well, our homogeneous fiber bundle is a fiber bundle over T mod S. And T mod S is a torus. Yes, T is a torus, S is some subgroup inside T. So the quotient is again torus. And if S is not equal to T, then it is not a trivial torus, not a point. So we have some invertible regular functions on T mod S. And if we denote by P the projection from our homogeneous fiber bundle to T mod S, then we can pull back this invertible function F, and we obtain an invertible function on X range. So it is a contradiction because we assumed that there are no non-constant invertible functions on X range. So actually here we obtain that T equals to S, but it means that our orbit Y actually is X range. This proof was communicated to me by Dmitry Timashov. My original proof was more complicated, but actually the situation here is rather simple. So actually, the main idea is that our set of smooth points X range is some SAut of X orbit Y, and it's not just some orbit, but it's a homogeneous fiber bundle with fibers isomorphic to this SAut of X orbit Y. And it's a fiber bundle over a torus, T not S. So let's now define these subsets XY, which we discussed before. So now let's back to spherical varieties. Let X be an affine spherical variety with an acting reductive group G, and Y is a G orbit which consists of smooth points. Let be a Borel subgroup and denote by d1 dk all B invariant prime divisors which do not contain Y. And so there is an open B invariant subset xy which equals to X minus all these B invariant prime divisors. So we excluded all prime B invariant prime divisors which do not contain Y. These open subsets play an important role in the theory of spherical varieties. So it's known then for not only for affine spherical variety, for arbitrary spherical variety, these subsets are affine open charts. But actually, for affine spherical variety, it's not just an affine subset, but actually it's a principal affine subset. I will not prove it, but actually it's, I think, it's a classical result. For example, in the famous paper of Knopp, Luna-Wüst theory of spherical embeddings, one can see not this lemma, but from from proofs of other lemmas, one actually can see that it's true. Actually, it's a principal subset. So denote by P the subgroup inside G, which preserves this subset XY. So the set of elements G such that GXY equal to XY. It is a parabolic subgroup because XY is B invariant, so B is contained in P. So for any parabolic subgroup, we have a Levy decomposition. So it's a semi-direct product L and some unipotent radical Pu. And there is a famous local structure theorem. Then there is a closed L invariant subset Z inside XY such that the map from homogeneous fiber bundle P times Z over L to XY, which sends the image of a point PZ to the result of the action of P on Z, is an isomorphism. So actually, this open subset is a homogeneous fiber bundle over P mod L. And moreover, it's easy to see that Z is a spherical variety with respect to the action of L. And it's not actually obvious, but it is can be proven that the intersection of Y and Z is a unique closed L orbit and in Z. So actually, Z is a spherical variety with respect to L, and it contains the unique closed L orbit. And since Y was a G orbit which consists of smooth points, then well, this subset Y, the intersection of Y and Z, it must be the points from this intersection must be smooth inside XY, but this intersection is a unique closed L orbit in Z. So any other L orbit in Z contain the closure of any other L orbit in Z contains this intersection. So it implies actually that Z must be smooth. And yes, and actually xy is isomorphic to a direct product of pu and z, because what is a homogeneous fiber bundle? It's in our case, it's fiber bundle over homogeneous space P mod L. But the important radical Pu acts on this homogeneous space P mod L freely and transitive. So actually, it's a trivial fiber bundle, and it's isomorphic to Pu times Z. So xy actually is just a product of Pu and Z as a variety. And as we know, any unipotent algebraic group is just as isomorphic to affine space. So this subset is a product of affine space and this spherical L variety Z, which is smooth. And now why the group generated by L and SAut of Z acts transitively on Z. And actually, essentially, it was proven again before in this paper. Let me go back. In this paper of Arzhantsev, Flenner, Kaliman, Kutzschebauch, Zaidenberg. So I mentioned before this theorem that if X is a smooth, irreducible affine algebraic variety and a semi-simple algebraic group Gx X on X with an open orbit, then X is flexible. But actually, if we will see at how the proof of this fact looks like, we will see that actually, basically, it is proven here that the group GS together with GA action acts transitively on X. And actually, that the fact that GS is semi-simple is not essential here. So we can consider a reductive group instead of semi-simple. But let me anyway recall the idea of the proof of this fact. So we want to prove that the group L generated by L and SAut of Z acts transitively on Z. I will recall that Z is a spherical L variety, is smooth spherical L variety. Denote by W the unique closed L orbit, which is the intersection of Y and Z in Z, and by H as a stabilizer in L of a point in W, of some point in W. Then we know that H is a reductive subgroup by Matsushima criterion. And actually, it follows from Luna et al. Slice theorem that there exists an H model V such that Z actually is a homogeneous fiber bundle L times V over H. And since we have an H model V, it's actually a vector bundle over homogeneous space L mod H. So Z is a vector bundle over L mod H. And obviously, L acts transitively on a homogeneous space L mod H. So we can any fiber move to any other fiber. And for any vector V inside a fiber V, there is a section S such that the value of the section at the point EH is V. Then we have the following GA action on Z. So an element T from GA acts on a point LW by the following formula. So just we add to W this vector S of L. S of L, it's some vector in the fiber. And we multiply this vector by T. And again, it's not difficult to see that it is actually a GA action. And by these GA actions, we can move transitively inside the fibers V. So these actions allows us to move inside fibers. And L allows us to change fibers arbitrarily. So we obtain that the group generated by L and SAut of Z acts transitively on this homogeneous fiber bundle. Well, actually, we didn't use that Z is a spherical variety. It's just we needed that it is a smooth variety with an action of a reductive group, and we have an open orbit with respect to this action. So sphericality here is not important. And so, as we discussed before, we obtained that for any G orbit Y, this subgroup, here I wrote generated by P and SAut of XY acts transitively on XY. But actually, we can change here for L as we did before. So yes, I think I mentioned the next lemma before, so let's not. Well, the proof of this lemma is not difficult. Here we need to use some theory of G action, correspondence between G action and locally nilpotent derivations, and one can prove this lemma. So, and actually, as I explained before, we obtained that this group G generated by G and SAut of X acts transitively on X stretch. And basically, it's finished the proof of main theorem. Okay, let me go to some further questions. Let me recall what is a root subgroups. Let X be an algebraic variety and let an algebraic group F act on X effectively. We say that GAA subgroup H in out of X is a F root subgroup if F normalizes H. So root subgroups, it is GAA subgroups which are normalized by this fixed sum algebraic group F. And when X is a toric variety, an acting torus with an acting torus T, the description of T root subgroups is well known by works of de Mazur for complete toric varieties and by work of Liente for affine case. And actually, the proof of flexibility, the original proof of flexibility for affine toric varieties, was strongly based on the description of T root subgroups. And in particular, it was proven that the group generated by the torus T and all T root subgroups acts transitively on the set of smooth points. For spherical variety, it's a natural consider B root subgroups. And actually, Avdeyev and Zhgun proved the similar fact for a quasi-affine spherical variety X with an acting reductive group G. The group generated by G and all B root subgroups acts transitively on X range. And actually, this theorem of Avdeyev-Zhgun, the variety X is not required to be normal here. And actually, this allows to conclude that the main results holds not only for normal affine spherical varieties. So the same true for non-normal affine spherical varieties. And one more question. For toric varieties, well, we considered, so basically flexibility implies that all smooth points belong to one orbit of automorphism group. Moreover, belong to one orbit with respect to the connected component of identity of the unit of automorphism group. And it is interesting to think about other orbits. Is it possible to classify all orbits of automorphism group or the connected component of unity of automorphism group. And for toric varieties, it was done by Bajov in complete case and by Arzhantsev and Bajov for affine case. They described the out of x orbits and out of x, zero of x orbits on toric varieties. And it will be interesting to describe all out of x orbits for affine and complete spherical varieties. And one more question. So we say that a variety X is a quasi-homogeneous if an algebraic group G X on X with an open orbit. There are examples of quasi-homogeneous affine algebraic variety X with a k of X range cross equals to k cross, but which are not flexible. But in these examples, G is not a reductive group. And there was a problem, which is, again, was stated before by Arzhantsev, Flenner, Kaliman, Kutzschebauch, Zaidenberg in their original paper, how to describe all flexible quasi-homogeneous affine algebraic varieties with an active reductive group G. Probably there must be some examples of quasi-homogeneous affine algebraic varieties which are not flexible, and the acting group is reductive. But I don't know any examples. So it is an interesting question. So this is all. Thank you for your attention.
Thank you.
Thank you, Anton. But you see that we see that your slides are not finished because it was a numeration at the corner. So
yes,
you have some extra slides.
Yes, but it is boring extra slides with the reference. So here I just listed some papers which I mentioned during my talk. Well, this is the work of Arzhantsev, Flenner, Kaliman, Kutzschebauch, Zaidenberg, which contains the main theorem about flexible varieties, and actually, and also this theorem about smooth quasi-homogeneous varieties, which I mentioned. And my talk was based on this work, which is not published yet, but one can find it on arXiv. Well, actually, one can find here all papers that I mentioned during my talk. So yes, and this is all slides. Thank you.
Thank you very much. So, dear colleagues, any questions, comments? Maybe I will ask a question. Can you go to the slide number 23?
Yes.
So you say that how do we prove flexibility of non-degenerate affine toric variety? You say that we consider T root subgroups, and we prove that the torus T and root subgroups altogether they generate some group which acts transitively on smooth locus, right?
Yes.
So I claim that torus is not needed. Only T root subgroups, only additive groups, they already generate a group which acts transitively on the smooth locus.
There's only in case non-generated.
Yes, for non-generated.
Yes, for non-degenerated, sure. Mm-hmm. Here you would like to cover also the degenerated case.
No. Here I thought about non-degenerate toric varieties. But I think you're right. Is it obvious? I just don't remember.
No, it's not obvious, but this is some proof that your root subgroup, they move points along the one parameter subgroup inside of the torus. So you imitate somehow torus action by additive groups.
Yes, you're right. Thank you. Yes.
Okay. Because torus, it has nothing to do with special automorphism. Special automorphism groups should be generated by additive groups. And so this is the way to forget about torus and to use GA subgroup instead of the torus.
Yes, exactly.
So
any more questions?
And then a reasonable question, if for a spherical variety you need only these B root subgroups, not G. Is it true?
Actually, I don't know. I think we need, I didn't see anything about it in the work of Avdeyev and Zhgun. Maybe I missed something, but I don't know. Is it enough to just to consider only B root subgroups?
I saw that Andrian was going to ask.
Oh, yeah, since we are on this particular slide and there is a definition, I'm always wondering what is meant exactly by a GA subgroup of Aut X, when GA is a group scheme and Aut X is just a group, right?
Well, yes, Aut of X has some structure. It has a structure of infinite dimensional algebraic group. So it's a kind. But I think this definition of a root subgroup motivated by root subgroups in reductive algebraic group.
Linear algebraic groups, I guess. Yeah.
Yes.
Yeah.
Yes.
Okay, so implicitly you are some kind of instructor on Aut X to speak about GA subgroup like being a closed algebraic subgroup of this guy.
I don't know. Maybe GA subgroups. To be honest, well, it's not obvious that they are closed inside the automorphism group.
Well, I can imagine non-closed additive subgroups. I mean, things whose closure is like higher dimensional in a sense.
Probably. Unfortunately, I'm not a very.
So you really want something which is represented by an honest GA acting algebraically on X when you said that, right?
Yes. Well, what precisely I mean by GA subgroup? Yes, I mean that GA acts effectively on X, and H is the image of GA with respect to this action.
Okay. Well, no, I understand. Okay, thank you.
You don't need any structure here on the automorphism group. You consider just all action of GA, algebraic action, and just images of this GA inside the automorphism group as an abstract group. And you generate by this image, by these images, a subgroup, which is a subgroup of abstract group.
I mean, this is probably just a matter of language. Aut X is just a group, and GA is a scheme. So, I mean, it's like saying a vector space is an algebraic variety. I understand that you map key points of GA to element of Aut X, but you want to say more than that. It's not just a morphism from K plus to Aut X in a sense.
You mean
and why don't you like to consider? Sorry, Anton, please.
Yes, I understand. So, kind of GA subgroup. It's not necessarily just abstract subgroup in Aut of X, which is as abstract subgroup is isomorphic to GA.
Yeah.
So kind of, but the definition is just the image of GA with respect to some effective actions.
Okay. Okay, makes sense. Okay, thank you.
So, any more questions? Maybe I will make one more comment, because for me the subject is very interesting. So assume you have some affine variety, and you want to know whether it's flexible or not. And you want to connect it with some actions of algebraic group. First step, completely obvious. When you have a semi-simple group acting on your variety transitively, then this is indeed flexible because any semi-simple group is generated by Gₐ subgroup. So some Gₐ subgroups act transitively on your variety. So SAut acts transitively on your variety. Next step, you have an open orbit of unipotent of semi-simple group on your variety. Then this is not so immediate, but for smooth variety, we can prove that this is again flexible. Then we come to the toric case. Open torus orbit has nothing to do with additive actions, with SAut and so on. But nevertheless, we have this technique due to Dimazur, to Liendo, with this root subgroup, and this helps us to prove flexibility. And then step by step, horospherical variety, and this time spherical varieties. So existence of specific open orbit of some semi-simple or reductive group guarantee that all smooth points are equivalent and can be moved to each other. So maybe the next point will be, as Anton mentioned, not necessarily spherical, but some open orbit of semi-simple or reductive group, whether it implies that all smooth points on our variety are equivalent, that we have transitivity of action of automorphous group on smooth point. And this is not known. But recently, Sergei Gayfulin constructed example of normal affine variety where SAut acts with the open orbit. The complement of this open orbit contains divisors. So you may have, this is not flexible variety, this is generically flexible. So you have an open orbit of group SAut, but this open orbit is not big. Its complement contains divisors consisting, for example, of smooth points. So it also can happen. But these examples, they are not related with semi-simple or reductive group actions. And this is very interesting to construct variety where semi-simple group can act with the open orbit, but the variety is not flexible. We believe that such examples should exist, but we cannot construct it. Okay, so if no more questions, comments. Okay, then
maybe I have a
let us
question.
thank Anton. Okay, Stephanie, please.
Okay, sorry. Maybe I missed something. What about the non-affine case or quasi-affine case? Is it solved here in the spherical case? Or this question of...
They are not always... yes, we need to...
main theorem. Do you have an analog in the non-affine case of your main theorem? Is it relevant?
We need to check. We need to recall the definition of flexible variety. By definition, it means that at any point, the tangent space is spanned by tangent vectors to Gₐ action on X. And actually, it is not true even for complete toric varieties. You can construct a complete toric variety without Gₐ action. So maybe one can find some criterion how by Flenner say when a toric variety is flexible, when a complete toric variety is flexible in this sense. But actually, I don't. Sorry?
There is no flexibility criterion or whatever this is called in general.
Yes, in general, there is no flexibility, yes.
Or maybe my question is not relevant because flexibility is only defined in the affine case or not?
Well, one can define flexibility for non-affine. But there is no such theorem, which was proved by Arzhantsev, Flenner, Kaliman, Kutzschebauch, Zaidenberg for not... well, actually, it's true for quasi-affine varieties, but for complete varieties, no, it's not true.
Thank you.
In varieties, we know that the connected component of the automorphous group is finite dimensional, so no chance for infinite transitivity. But Anton, returning to this question,
this
our
means
theorem
that for any proper variety cannot be flexible then.
Because
right?
finite dimensional.
The automorphism group functor is representable, so the neutral component is an algebraic group, 5-dimensional in particular. Right?
Yes.
But Anton, returning to Stephanie's question, so this our theorem, which you have on the screen, it was later generalized to quasi-affine variety. And your theorem holds for quasi-affine spherical varieties.
Yes, actually it holds. Yes, my original proof was for affine, but as Avdeev and Zgun, they showed actually that for quasi-affine varieties it also holds.
Okay. As during the legal process, I should ask whether we have any more questions or comments. If not, then many thanks to Anton for his talk, and we continue in June and even in July. So we welcome you to attend 2 more seminars in this year, not calendar year, but this, how to say, academic year. We will have seminars in June and July. So thank you very much for being with us. See you.
Thank you, Anton. Goodbye.
Thank you.